Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today's video is inspired by some other guy on the internet, on YouTube, that created a very neat continuity tester. And I stumbled on his video a while ago, and since I needed something like this for myself, I decided to basically take a bit of inspiration from his design and use it to design and create my own continuity tester. My needs were a bit different than his. I needed a continuity tester just because I was using an older half-broken multimeter just for the continuity tester, and it was occupying space on my workbench, and I kind of didn't like the idea of, having that space occupied only for a multimeter that does only continuity testing, because other than that it's not capable of doing anything else. So when I saw his video, it was a very nice thing to find his video and his design, because I immediately decided that I need something like this for myself. And this is what I'm going to be presenting to you, because I've designed it, I've completely built my own continuity tester, at least as far as the electronics are concerned. I still need to 3D print a plastic cover and a few other things, a few minor things that need to be done, but those are just on the physical level. The electronics level is 100% complete, tested, it works as I wanted to, and so this is what I will be presenting to you in my video. Now, I've already done a video like this with my continuity tester in Romanian, and it took almost 2 hours. So go grab a beer or a coffee or popcorn or whatever it is that you are consuming during very long videos, because, like in many other of my videos, I like to explain everything that everything that is necessary to build that device, to understand how it works, why things are there and not in some other places, and so on and so forth. Sorry. So it's gonna take quite a while for me to go through each and every aspect, but I consider it worth the pain. So let's dive into it. This guy's schematic was something like this. You can find it in his videos. Again, I will post a link to his video in the description. It's a relatively simple design that in the end just turns on a LED and makes some noise with a beeper, with a piezoelectric beeper. For him, that was enough, so okay. For me, on the other hand, it's not enough. I decided that, no, it's a bit too little for me. I need something more. So I had a few requirements that were like his, and a couple of requirements of my own, which led me to need to design my own circuit. Okay, just like in his case, I agree with the idea that continuity is something around 5 or 6 ohms, not 50 ohms like he showed in his multimeter. I've tested my own multimeters, the ones that I own, and they consider to be continuity anything between 30 and 60 ohms, depending on the model. Yeah, so that was one of the requirements that he had, and that I also agree to take as part of my requirement as well. Continuity is something around 5 ohms or less. So a continuity tester should make it clear that we are having 5 ohms, around 5 ohms or less. And another requirement that he had, and that I agree with, and so I adopted it as well, was that we should be able to insert voltages on the input, and the device itself should not self-destroy. And it should also not be a problem for us as humans, as operators of the device, okay? And he used a rather exotic, or what I would call an exotic component, electronic component, transient blocking unit from Borns. Okay, I guess for him it did the job. Personally, I would prefer if I would not have to use such an exotic component. It's not difficult to obtain, it's also not very expensive, it's $2 a piece, but if there would be other options that would not require something like this, I would prefer to go with those other options, okay? So this is kind of half of a requirement that I have taken over from him, but I've modified it in my own way. On top of what he created for his continuity tester, I needed more in terms of functionality. You know, I don't like the idea of having just one LED and that's it, okay? For me, that was just not good enough. And so I created a design that has 10 LEDs. Each of them light up at different values of resistances, and the piezoelectric beeper beeps at around 5 or 6 ohms, just like in his case. And on top of that, if we apply a voltage on the input, which we shouldn't, but if we happen to accidentally apply a voltage on the input, I would like to see that. So I would like to have different LEDs that light up when I have a voltage on the input instead of resistance. Okay, so those were my extra requirements. And in terms of physicality, I wanted a case that can be sealed almost watertight, as watertight as possible. So I didn't go with his design of a case with banana jacks on the input. I went with some other ideas, but I cannot show them to you because, like I said in the beginning, I haven't completely finalized the physical aspect of putting it all together. What I can say about is that I've designed a case that has no holes other than the ones used by LEDs, and the LEDs can potentially be insulated with some glue so that water cannot go inside the case through the holes of the LEDs, and also the top cover can be insulated with a rubber band around the case. Okay, so that was my extra requirement, so that the idea was that if I will ever need to use this device outside when it rains, I shouldn't have a problem with it. Okay, anyhow, that's a small aspect that doesn't matter all that much. So let's dive into the inner workings of my design, and let me show you what I built in the end, which required 2 boards, or well, it didn't require 2 boards, but I built the whole circuit split in two different boards so that I can test them individually and I can make sure that they work individually. It was an easier job for me to do. Anyhow, let's get into the details of how my continuity tester looks like, which, yeah, it's a lot more complex than his. I do admit it, yeah, for some of you it might look a bit scary, but trust me, it's not scary at all. It's not it's not difficult to understand. You just have to have a little bit of patience to get to understand every component here, what it does, why it does that. Now, before we move forward, I just want to mention the fact that there are a few things that I'm not going to be discussing in this video because I've discussed about them in previous videos of mine. Okay, so the video immediately before this is called signal conditioning, and here I presented a few methods of taking a signal that looks in a certain way and basically converting it into another signal that looks in a different way for particular purposes. And also the previous video before that was about various unwanted signals that come from power cables and can get to injected into our circuits if our circuits have a high impedance. Okay, so I won't be diving too deep into those matters. I will just cover them briefly when the time comes. Now, the whole circuit, as we can see here, can be displayed into can be divided into three different pieces. We have a piece that we could call front end because it has the input connectors attached to it, and its purpose is to basically convert well, it has actually multiple purposes, but the main purpose is to convert the input resistance, because essentially when we're testing continuity, what we want to do is essentially measure a relatively small resistance. Okay, so the front end, the main purpose of the front end is to convert this resistance into a meaningful signal that we can work with later. Okay, that's the main purpose. The secondary purpose is to protect both itself and the rest of the circuit from input voltages, especially from high voltages. The third purpose is to basically let us know when we have a voltage on the input by lighting up one or two LEDs or both, depending on the case. We will see towards the end of the video. I will make some demonstrations. Well, I've already recorded them, but I will present them to you and I will explain. And a fourth, but still important purpose of this front end is to provide or cut power to the rest of the circuit so that the whole device has a very low current or a standby current when we're not connecting anything on the input. Okay, and when I say low current, I mean I've measured it to be around 6 microamperes. Okay, and 6 microamperes is quite a low current to have. In order to put things better into perspective, in one of my previous experiments that I haven't shown on this channel, I have come to realize that a double A battery, 1.5 volt battery, has around 3 watt-hours of energy in it. Okay, so for this device I'm using 3 batteries. Leo was using only 2 batteries. For me it was just not enough. I had too many voltage drops due to all sorts of components here, so I needed an extra battery. So I'm using 3 batteries. If each battery has 3 watt-hours, then all 3 of them have 9 watt-hours. If we divide 9 watt-hours by the standby current multiplied by the voltage, so 4.5 volts multiplied by 6 microamperes, so that's 1, 2, 3, 4, 5, 6. This results in 333,000 hours of standby from a set of batteries, provided that the batteries themselves don't discharge themselves over time, they don't leak. Okay, provided that the batteries are capable of functioning 333,000 standby hours we can get from them with this device. Now, this is not very useful, so let's divide that by 24 hours a day. It's still a large number, divided by 365 days a year. This means that this device can stay in standby for 38 years without us needing to change the batteries. Yeah, I don't know about you, but that's pretty much my age right now. You know, I have 37 years. 38 years is basically like I can't even conceptualize having something that will still work after 38 years and me actually still needing it after 38 years. So yeah, so this front end overall does a good job of obtaining a very small standby current. Okay. Other than that, we have a second stage, which we could call signal conditioning. It's a stage that takes the very small signal from the front end and amplifies it, and also does some tricks with it, so that later it can be fed into the display section of the circuit, which uses LEME 3915 integrated circuit that is able to drive 10 LEDs. It's pretty much a VU meter, right? That based on input voltage and a reference voltage, it is able to light up some LEDs from here or light up all of them. And because we want to have an acoustic signal as well, you know, we have a derived small circuit from here that powers a buzzer that just beeps, you know, whenever it is needed. So the majority of the discussion from now on, I will be talking about the front end, because the front end has only discrete components. It cannot have integrated circuits because the vast majority of integrated circuits cannot withstand hundreds of volts. This circuit must withstand hundreds of volts. So yeah, I needed to use only discrete components, and so I need to explain them to you, what they do, why they do like this, and how did I came to have this entire circuit, and why not something simpler? Because this is the actually this is the absolute simplest circuit that we can potentially have here. Okay, so let's dive into it. In order for me to explain the front end, I need to make use of other circuits, and I have drawn 5 different circuits. Basically, we're taking it step by step, and we are seeing what exactly do we need and why do we need to complicate things, because we need to solve some other problems. Okay, so what would be the simplest form of testing continuity? Well, if continuity for us is a resistance, which is represented here by this resistor here on the lower side, we are taking at the first stage, the first phase of our design. We have a resistor here that says to test. That's our continuity that we want to test. So basically that's the external thing that we are connecting our tester to. The simplest form would be to take a battery, to connect one wire to that particular device, and the other wire from the battery, pass it through a resistor and have that resistor into the other side of the device or cable or whatever it is we're trying to test. This forms a voltage divider, and basically this would give us theoretically a voltage relative to ground that is low when we have a good continuity, meaning a low resistance, and it's relatively high when we have higher resistance, which equals worse continuity. Okay, there are several problems with this, and so needless to say we need to complicate things. So one problem is that since we're trying to measure very small resistances, the higher this resistor we place here, the lower all of the voltages that we will have as signal will be here, and the lower these voltages are, the harder it will be for us to work with them. Okay, another problem would be that if we decrease this resistor in order to, you know, have higher voltages, we would be injecting too high current in some circuits, and we will be causing problems. Also, we will need to have a power supply that is able to provide a relatively high amount of currents. I don't know, potentially in the hundreds of milliamperes. That would be too much. At least for batteries, for most batteries, that would be too much. So it wouldn't be good. And yeah, this resistor would also need to be a relatively high power resistor. On top of that, we have pretty much no chance of protecting the circuit against voltages on the input. So yeah, this kind of gets thrown out the window because this is just not good enough. Okay, how can we solve at least one problem? Well, how about we have a constant current through the device that we're testing, and this current is small enough that it doesn't cause us problems, high enough that it does generate a voltage that we can use later. So how about we do that? We inject a constant current. A problem with the first stage, the first option that we have with just a resistor, is also the fact that the response of the signal will not be linear with the resistance. Because the higher the resistance will go, the less the voltage will increase. The lowest voltage is basically 0 volts, but the highest voltage that we can have here is just the power supply, the batteries basically. So as resistance increases here, the voltage will increase, but it will not increase linearly. You know, the overall response will be a curve, and this is kind of a problem for us. We would like to have a linear response, okay? And a linear response can be solved with a constant current circuit. So let's move on to the second stage, where we basically replace this resistor with a constant current circuit. And the simplest, well, not the simplest, but the second simplest constant current circuit involves 2 transistors and 2 resistors. The upper transistor gets to be turned on by default by this upper resistor, and it starts to pass a current, but it passes a current through this lower resistor. When this lower resistor develops a voltage across it that is big enough to open this second transistor, this one will drag the base of the first transistor down, and it will tend to shut it down. And this is how it will regulate the current that the first transistor provides to the entire circuit. Okay, and this is how we obtain a constant current source. So if we inject let's say 10 milliamperes, which is the value that I've chosen in the end, into our resistance, considering in my case I chose to measure resistances anywhere between 0 and around 20 ohms, this will give us anywhere between 0 and 200 millivolts of voltage to work with. This is good enough, okay? It's good enough that we can basically work with most op amps. They have an input offset voltage of a few millivolts. A few millivolts is kind of similar to 1 ohms, give or take. So overall, this is a good solution. It's a good choice. So we have basically solved one problem. Now we have a voltage that grows linearly with resistance, and the current that we feed is small enough. It's not a problem. It is achievable by using batteries. So perfect. However, we still have some other problems to solve. And the biggest problem is the fact that this circuit is not protected at all from input voltages. Instead of on the input we don't have a resistance, we have a voltage. Well, the circuit is not protected at all. So we need to dive into that problem, because right now we have one problem solved. The problem of how we convert continuity into a voltage, resistance into a voltage, okay? So from now on we will be basically dealing only with the problem of protecting the device. So we can do a couple of things in order to protect this device, which are pretty much similar to you know, what Leo did in his design. Let's say that we have voltages instead of resistance on the input, okay? We can use a rectifying diode in series with a current source, a constant current source, to essentially prevent a voltage that has the polarity plus on the input wire and minus on the ground of the circuit to enter through the rest of the circuit, okay, and to pass through this constant current source in reverse. This voltage, this diode protects against that without a problem. Of course, the high voltage, or the voltage, whatever it may be, can go further to the rest of the circuits that do the other work. However, that's also a relatively simple problem to solve, because we can place a relatively high value resistor here in series with the output and place a rectifying diode like this upper rectifying diode between the output and the positive rail of the batteries. This way, this diode will basically clamp the output voltage to only a diode drop above the input, above the power rail, and it will keep everything on the output in reasonable limits, okay? Now the problem, so basically this problem with the voltage with this particular polarity, okay, so let me delete this for a moment. This problem gets solved when we have a voltage like this with positive up and negative to the ground. However, this does not solve anything for when we have a reverse voltage. We can do one thing in order to start protecting us from reverse voltages, but it will not be enough. And the first thing that we can do is to add another protection diode like this between the output and the ground. This will make it so that current will want to pass through it, because it will be a lower resistance path, and it will pass through it and go back through this resistor to the source. But then current will also be able to pass, some current will also be able to pass through the next diode to go up to the positive power supply rail, well, the positive rail of the batteries, to pass through this constant current source, through this other protection diode, and back to the negative pole of the input voltage. So, okay, we have protected the output, because the output can never go negative by more than a diode drop. However, we still have a problem with this constant current circuit, because it will get blown away. Having 10 milliamperes constant current at some 300 plus volts, that's just not good enough, and that's a huge problem. What can we do about it? Well, what's the problem actually? First of all, we need to use high voltage transistors here, okay? So we cannot use the regular bipolar transistors that we use in everyday projects. We have to use high voltage transistors. That's not a problem at all. I have found MPSA 44 to be a good choice for such an NPN transistor. It can be found in sufficient quantities on the internet. It's relatively cheap. It can resist a collector to emitter voltage of up to 400 volts, a collector to base voltage of up to 500 volts, and it has a power dissipation of 600 milliwatts, maximum current 300 milliamperes, collector current. It's way more than we need, so overall this is a good choice. That's the first thing that we need to do here. However, it's still not good enough because the dissipation power would just be too high. Okay, if we have I don't know, 240 volts, the peak voltage would be around 340, provided that it doesn't go above by mistake. Basically 340 multiplied by 10 milliamps, that's about 3.4 watts of power that this transistor would need to dissipate, and they cannot. Like I said, these transistors have 600 milliwatts maximum dissipation power, and that is at ambient temperature. The more they heat up, the less the power they can dissipate. So anyway, we need to solve that problem. But what is dissipation power? Well, dissipation power is nothing else but voltage multiplied by current, basically the collector to emitter voltage multiplied by the collector current. So if we can drop these two or one of these two down to zero or close to zero, then we no longer have power to dissipate. We cannot drop the voltage, but we can drop the current. And basically what we need to do is to shut down, whenever the voltage becomes too high, we need to just shut down this constant current source so that no current flows through it, so that the power dissipation power drops dramatically. Okay, this is something that we can relatively easily accomplish by basically placing another transistor here. I'm not gonna wire it completely, I will show you in the next phase. In order to turn off the current on this constant current source, we need to shut down this upper transistor. Okay, so to shut down this upper transistor, we need to take its base and drop it down to the ground as much as possible. We don't need to do that too much, just a little bit so that it turns off. And we do this with another transistor that is placed sort of in parallel with this lower transistor, and that gets to be turned on whenever the reverse voltage through the circuit reaches a certain level. And for that we can use the voltage drop on this resistance here in order to monitor, you know, in order to monitor this reverse voltage and turn on this transistor, which in turn turns off this upper transistor, which basically means no more current passing through the constant current source. Okay, and this is basically what we see here in stage number 4. In stage number 4 we have added this transistor, which requires its own protective diode, so that whenever we have a voltage with a plus on the upper side, current does not pass through it. Okay, and the base, it's connected to another resistor here. Basically we have taken this resistor here and we have split it into two resistors, one of relatively lower value and one of higher value, so that whenever we have a reverse current through here, we also have a reverse voltage on this resistor, which in turn turns on this transistor. Okay, and by turning on this transistor we are effectively shutting down the constant current source. Okay, perfectly, but we still have a problem, and that is if we let here only one transistor in the constant current source in the upper side, it's still gonna blow this third transistor that turns it off, because when this transistor starts to conduct, there will still be current flowing through this resistor here from the relatively high voltage, right, through the diodes, through this resistor here. maybe, okay, maybe I should draw it a little bit. So whenever we have a voltage like this here, we have a current that passes through this diode, it can go through this resistor, and it cannot go through here because this is turned off. Okay, this is also turned off, so it cannot go through here and through this diode. However, it can go through this resistor and then through this transistor, which is turned on in order to pull this down, and through this diode that I haven't shown here, this other one here, right, back to the negative pole of the input voltage. Which means that both this transistor here and this resistor here will be needing to dissipate some power. Okay? What kind of power? Well. Let's calculate. If we need a 10 milliamps current through this constant current source, and we have chosen MPSA 44 transistors, by looking into its datasheet, we can see, I've extracted these informations from the datasheet. We can see that the beta, the factor of this transistor, of this model, at 10 milliamps is as low, or can be as low at 50. Okay, so in other words, if we need 10 milliamps, collector current divided by 50, we need to inject at least 200 microamps into the base of this transistor. Okay, so let's consider that we have about 3 volts voltage drop on this particular resistor. Okay, we have anywhere between, I don't know, 2 or 3 volts, because we have 4.5 volts from the batteries, minus some collector emitter voltage on this transistor, minus 1 diode drop, minus the voltage on the input resistance, on the input that were the resistance that we're trying to measure the continuity. Anyhow, let's say 3 volts for the sake of simplicity. We don't care that much right now about precise values. So if at 3 volts we need to generate 200 milliamps, this means that we need to have a resistance of about 15 kilo ohms. Now 15 kilo ohms sounds like a relatively high resistance. However, it's not that high when we have to when we are placing a relatively high voltage across it. So if we have 340 volts divided by 15 kilo ohms, it means about 22 milliamps of current flowing through that resistor, plus the transistor that the extra transistor that turns off the constant current source. This is a bit of a problem because, well, both this resistor and the associated transistor would need to withstand or rather dissipate, how much was that? Voltage squared over resistance, yeah, sorry, 340 squared divided by 15 kilo ohms. They would need to dissipate around 7 volts or so, 7 watts, sorry, or so of power, and this is just way too much, both for the transistor and for the resistor. For the resistor we would need to use a power resistor. It's still not good enough because it will the transistor himself cannot withstand that much power, so we clearly need to have a lower current flowing through here. Okay, but that's a bit of a problem for this particular circuit, because a lower current in the base means that this transistor will probably not be able to open enough to provide 10 milliamps of constant current through the rest of the circuit. So we do need a relatively high current. Well, high, it's relatively speaking. So we do need a certain resistance here. How can we solve it? Well, We can solve it by, instead of having a single transistor here, having a Darlington pair. Because whenever we are having a Darlington pair, we are essentially multiplying the two amplification factors. So a single transistor having an amplification factor of 50 means that two of them in a Darlington pair would have a 2500. Okay, 50 multiplied by 50, that's 2500. And 2500 is a lot better. Okay, if we divide 3 by the base current obviously it will be a lot smaller, 10 milliamps divided by 2500. This means that we can use a 750 kilo ohm resistor here in the base, and that's much better. In practice, I've actually chosen to use a smaller value, 1/3 of this value, 240 kilo ohms, and 240 kilo ohms is enough to inject enough current into the base of this Darlington pair to turn it on, to provide the necessary current, constant current, and as well as when this transistor turns on, in order to shut the constant current down, the current flowing through this whole thing will be a lot smaller. So I've chosen 240 kilo ohms. Let's see, 340 volts squared divided by 240 kilo ohms means that we will have only half a watt of power dissipated in these two components. Half a watt of power is good enough for both the resistor and the transistor. We can use half a watt resistor if we want to, not a problem. The transistor himself has a 625 milliwatts of dissipation power. So yeah, this definitely solves this other problem. So this is how we essentially get to phase number 4, where we have 4 transistors and all of these other components. Now we still need 2 more things, or I still needed, we need at least one more thing, and I needed an extra thing on top of that. We still need to, for this circuit, to turn on and off the other circuits. Okay, and personally, since I'm doing this sort of detection of over voltage, I thought, why not have some form of signaling, some LEDs that just light up, okay, to clearly show me that I have a voltage on the input. And this is why I have moved on from this particular design into complicating it just a little bit more. And this is the final result of the front end, where on top of these components we also have these on the bottom. We have 2 transistors that individually turn on different LEDs. Okay, so when we have a positive voltage on the input like this, so we don't have a resistance to measure continuity, we are applying a voltage here. We can turn on an NPN transistor through this voltage divider here and this protection diode here. We can turn on this NPN transistor so that this NPN transistor will connect, will turn on this LED. Okay, we have a current that starts from the battery, enters this limiting resistor, and then through this LED and this transistor turned on completely, it gets to be connected to the ground and then return to the battery. So whenever we have an over voltage here like this on the input, we have one particular resistor LED, sorry, lighting up. And for me, that's a green LED. I chose to have a green LED here and a red LED for the exact opposite polarity. So if we have a voltage like this with a minus up and plus down at the ground, Then we have an NPN transistor that can light up, that can turn on, okay, because it is polarized accordingly. We no longer need a voltage divider. We needed a voltage divider for the NPN transistor so that it would not turn on during normal operation, okay, when we just have the voltage from the current source, from the batteries. We want this to turn on only at voltages, you know, well above the battery voltage. So we needed a voltage divider here for the PNP transistor, sorry, that gets to be turned on when input voltage is reverse polarized. Then we don't need a voltage divider. It's enough to have a limiting resistor and a protection diode like this, and this will get turned on, and it will essentially do the same thing, only with the other LED, which in my case is red. Okay, a LED that gets connected to the ground, and that basically has the current has a path through to flow from the batteries through this resistor and through the red LED, and this is how I will know that I have a reverse voltage on the input. And if we have an alternative current, an alternative voltage on the input, then we will have both of these LEDs turn on at the same time. They will, technically speaking, be blinking, but you know, 50 or 60 hertz, it will be invisible for the human eye. We will see them both as being lit at the same time. So this is how this front-end circuit tells us whether we have a resistance on the input or a voltage, and what kind of voltage. Okay. What next? We want to have the circuit turn on and off the power supply for the rest of the circuit. Just like in Leo's design, we have a PNP transistor here that has a base connected to a resistor, to another resistor here in the collector of this Darlington pair. So basically, unlike in the fourth stage of our development, when we have the collectors of both transistors from the Darlington pair connected directly to the positive supply rail, right now here we have them connected to another resistor to the positive supply rail, so that we have a certain voltage drop, so that we can monitor that voltage drop and turn on this particular resistor here. Okay, basically, whenever we don't have anything connected to the input, the current flowing through this whole thing will be so small that the voltage drop across this resistor will be basically nothing, and this transistor will be turned off. When we will have something connected to the input, current will be able to flow. If we have a 10 milliamp constant current through the circuit, then we will also have a constant voltage across this resistor, so we will be able to rely on it to reliably turn on this PNP transistor, which will in turn power the rest of the circuit. Okay, so this solves this other problem. And we also have a bit of an extra problem that I haven't mentioned so far, which is the fact that if we would have this circuit like this connected straight to the battery, well, the voltage that we would experience here on the output, if we would place a voltmeter here on the input, sorry, not on the output. If we place a voltmeter here on the input, we would see a significant voltage that is a bit too high. And when I say a bit too high, you know, normally 4.5 volts or around 4.5 volts is not a high voltage. However, if we accidentally place this between, I don't know, the input or the output pin and the ground of an integrated circuit, a digital integrated circuit that works with 3.3 volts only, we have the chance of burning that integrated circuit, because there are some circuits that do not allow more than 3.3 volts to be applied to their inputs or outputs. And that's going to be a problem, and we don't want to blow up components accidentally by just poking around our continuity tester. Okay, we don't want that to happen. So in order to solve that problem, we need to drop the voltage that we see on the input. And the only way we can do this, or the only way that I found we can do this, is to basically have another diode here that will, well, essentially drop the rest of the voltage for the constant current source and subsequently for the input connectors. Okay, this is why there is this diode here. And be careful, because this protection diode here must be connected straight to the positive rail of the battery. And so this diode here that just drops the voltage for the constant current will have to be after that. We cannot connect these two cathodes together, because this protection diode will no longer work anymore. Okay, so the placement of these diodes is critical to be like this. Okay, so this is the logic behind the front end, and why does it looks like this? Okay, why are all of these components like this? Yeah, why is everything like this? Why don't I have less components, and so on and so forth? One more mention before we move forward to the rest of the explanations. Only these 4 transistors here have to be high voltage transistors. The rest, the other 3, can be normal transistors, low voltage ones. Okay, in my case 2N something. So because the other 3 transistors never see a high voltage, never, no matter what, so they can be just regular transistors. These 4, on the other hand, must be high voltage transistors. Okay, so now that I've explained you know, the overall logic, let me show you some values for these components that I've chosen here, and then let's move on, because we have quite a few more things to talk about. So we need to have here between the input and the output a separation resistors that have a relatively high resistance. I've chosen around 1 megohms. Okay, so we have these two 560 kilo ohms resistors. I've placed 2 of them in series instead of just one resistor of 1 megohm resistance, because resistors have a maximum voltage that they can work with, and that's 250 volts for 0.25 watt resistors. Yeah, it's a bit too low for this particular project. So because here we will have considerable voltages between these 2 points, we need to make sure that there's no resistor that will just short circuit and blow up our circuit, because we have applied too high voltage at its terminals. And by the way, it's not a matter of power of dissipation, it's a separate, completely separate problem. Okay, so we have 2 560 kilo ohm resistors, another 100 kilo ohm resistor here in order to detect reverse voltages, in order to, you know, turn on this T4 transistor that shuts down the constant current source. We have here 2 more resistors. In my previous presentation I only had 1, but for the exact same reasons, here we will have, between these 2 points, we will have high voltage whenever we have high voltage on the input. So in order for this resistor not to blow up, we need to put 2 in series, each of them resisting 250 volts. So yeah, they both can withstand quite a lot together. These lower resistors I have determined experimentally. They haven't truly been calculated. We need high resistances here overall, because especially for this NPN transistor, because we need voltage divider. We don't want this voltage divider to be interfering with the rest of the circuit, because this voltage divider essentially keeps these 2 points constantly connected to each other. but these 2 points are also the input points, the input connectors. Well, we need to have super high, a high resistance, so that the current flowing through it will be very small, so that, you know, this constant current source will not actually be functioning, and and so that we don't have a high current draw from the battery. 1 mega ohm resistance in series with 270 kilo ohms seems to do the job for this particular branch of the circuit, and the PNP part of the circuit does not need a voltage divider, because we can just turn it on in reverse voltage. We can just turn it on as soon as possible. We still need a 1 mega ohm resistor or around 1 mega ohm resistor in order to limit the current through T7 when the voltage on the input is relatively high, so that T7 does not experience a high base current. Okay. What else? This 270 ohm resistor has been chosen to limit the current through the two LEDs. Okay, so we have here we have basically a collector to emitter drop voltage, plus of course the voltage drop on the LEDs themselves. So we have 4.5 volts from the batteries minus some half a volt. We see that the collector emitter saturation voltage at 10 milliamps is about half a volt for this type of transistor. So we need to subtract this half a volt and minus 2 volts for the LEDs. This leaves us with just 2 volts divided by 5 milliamps, means a resistance of around 400 ohms. I chose to put a smaller resistor here to make the LEDs turn on a bit more. These are actually 10 milliamps LEDs, so yeah, I'm just choosing to feed them with a smaller current, so that it's not a problem, you know. Okay. Other than that, I've shown you how to calculate R1, R4 before. These two other resistors need to be mentioned, R2 and R7. Now, R7 I have determined experimentally to have a need to be 33 ohms. Normally, this would be calculated by dividing the opening voltage of this transistor, which is around, I don't know, 0.6 volts, to the current that we want to have through the constant current source, which is 10 milliamps, which would require about 60 ohms. However, I've seen that 60 ohms is a bit too much in practice, so I needed to lower this particular resistor in order to get as close as 10 milliamperes as possible. Okay, so this is how I came to the conclusion that this needs to be 33 ohms by just practical experiments. Let's explain this R2 resistor, and in order to explain it, we need to basically make a new drawing and explain to you the voltage drops that happen here, because in order to determine its value, we need to know the current that flows through it, which is 10 milliamps. We know it because it's part of the constant current source path. Okay, but we need to determine the voltage across it, otherwise we cannot truly calculate it. And partially this resistor serves also as a way to take away dissipation power from these transistors. Okay, because the higher the voltage drop that we allow on this resistor, the lower the voltage drop on this transistor, and therefore the lower the dissipation power that it will need. So we have a 4.5 volts battery, okay, that allows current to flow through here. And let's see what voltage drops we have so that we can deduce the voltage drop on R2. Well, we have a first voltage drop here. We have, of course, the voltage drop on this resistor, but that's given, you know, that's what we want to find out. We have collector emitter, a saturation voltage for T3. We have a voltage drop here, which is, well, pretty much known. We also have a voltage drop here, and on this protection diode D6, and of course we have the voltage drop on the input pins, which is dependent on the input resistance. Okay, so let's calculate. 4.5 volts minus, what exactly voltage drop will we have on this diode? Well, it's not going to be 0.7 volts actually. If we take a look at the 1N4007 data sheets, at some point we will see a graph plotting forward voltage with forward current, and we see that at 10 milliamps we have 0.6 volts of forward voltage drop. Okay, so it's 0.6 volts. We have 0.6 here on this diode. We have yet another diode like this, so another 0.6. I'm taking them in the order in which I can calculate them as easily as possible. The voltage drop on the input will be a maximum of 0.2 volts because I want a maximum of 20 ohms to be measured, and 20 ohms multiplied by 10 milliamps, it's 200 millivolt voltage drop on it. So 0.2 and minus the voltage across this resistor, which should be 0.6 volts normally in order to open this transistor. On the other hand, you know, if we have a 33 ohm and we are passing 10 milliamps through it, then we are having what, 330 millivolts. So yeah, I don't know what to choose. Let's say 330 millivolts, so let's say 400 millivolts. Okay, 0.4. That leaves us with 2.7 volts divided by 0.01, 10 milliamps. Okay, that's 270 ohms. However, I've chosen, for the sake of being sure that we don't have a too big resistor that creates problems for the transistors, because the transistors will not be able to provide enough current even if they are turned on to the maximum. I've chosen a smaller resistor than this. I've chosen 180 ohms, which basically at 10 milliamps through it allows a current, forms a voltage of 1.8 volts across it. So we have 1.8 volts here, and we have another 0.6 on this diode, and both of these voltages are seen by the emitter to base junction of T2 transistor. Okay, so whenever we have this voltage, we can turn on this transistor. Whenever we don't have this voltage, this transistor will stay shut down. So 2.4 volts. Okay, so we have 1.8 plus 0.6. Yeah, I said correctly, 2.4. If we divide it through to the minimum current that we need to insert in the base of T2, then we will get the value of this particular resistor that we need to set here. And the minimum current is basically, well, we need a collector current of around, I don't know, 30 milliamps or so. So let's say 30 milliamps divided by, what's the beta factor of this transistor? Well, I chose 2N3906, and at 50 milliamps it tells us that it has a 60 or above. So let's say the minimum of 60 amplification factor means that we need about 4.8 kilo ohm resistance here. I've chosen to put a smaller value resistor to be able to be sure that we are injecting a good enough current in the base, so that T2 will open completely and it will provide the necessary current to the rest of the circuits. Okay, and yeah, basically this is how the front end was created and why it was created like this. So now that the front end works correctly and is able to power the rest of the circuits, let's dive into signal conditioning and the display section of the circuit. Okay, so if we have 10 milliamps through a 0 to 20 ohm resistance, we have basically a signal that goes from 0 or close to 0 all the way to around 200 millivolts. This is not a good enough voltage for us to work with. The signal is just too small, so we need to do something about it. However, we also have another problem at hand. Because of this high resistance values between the input and the output of the front end, we are having a high resistance, high impedance circuit that picks up all sorts of interference from the outside world, from the power cables in the walls and devices around us, and that's creating a problem. So our signal is basically a DC level, on top of which there is superimposed an AC voltage. And it's typically 50 hertz or 60 hertz depending on where you live on the world. Well, we need to remove that 50-60 hertz signal, and in order to do that, we basically need first to apply some filters. So I've placed a 100 nanohm capacitor here. It does some filtering, but it doesn't do it well enough. I cannot put a bigger capacitor, because then it would severely impact our signal. So 100 nanofarads is the most I can place here, but we need some extra filtering. So after we have filtered this this signal a little bit, I am sending it through a buffer, and at the end of the buffer I am applying a new RC low pass filter, but this time with higher values of components, because it's not a problem anymore. We don't have high impedance anymore at the end of the first op-amp. Okay, and we are filtering this even more. So basically, in order for me to explain to you this a little bit better, let me draw. In this particular point, we have a voltage that is both small but also has a pretty high variation. In this particular point, we have a voltage that over time is also small but has a smaller variation. It still has a variation, but smaller. Okay, we still want a higher attenuation of this unwanted signal, so we're passing through this buffer, through this RC filter, and then gets inserted into the next op amp. And here in this point we basically have a voltage that is still low, but that varies much less, and it's much easier to work with this signal here. Okay, this op amp is in non-inverting configuration, just a simple non-inverting amplifier, and so in this point here we have an amplified signal, okay, that we can better work with. And here the third op amp does a reversal of everything, and also it's sort of how should I say it? It transforms a linear response on the input into a reverse logarithmic response on the output, and I'll explain in a moment why we need that. So this op amp, basically, if we have an input signal that grows like this, it gives on the output an output signal that grows, that shrinks kind of like this. So whenever we have whenever we have low input voltage, or we have high output voltage, and whenever we have high input voltage, we have low output voltage. And the overall curve is not linear by far, it's actually kind of a reverse logarithmic curve. Okay, I won't go too much into details about this circuit because I have talked about it in the previous video that I made on my channel, just the one before this. It's called signal conditioning. I have presented here 5 different circuits. I am using the 5th circuit from that video. Okay, so if you want to understand how this particular op-amp works with the associated components, go check that video out and you will understand. Now, to explain to you the reason why I needed to do this, well, the problem is for us high continuity, a good continuity means low voltage, and because low resistance provides a low voltage for our signal, and a high resistance, which is associated with you know, a low continuity, gives us a high voltage. I wanted to feed LEMET 3915, which is a logarithmic 30 decibel 10 LEDs integrated circuit, and so I wanted all of these LEDs to be turned on when I have the smallest resistance on the input, therefore the smallest voltage. But then it's when this integrated circuit requires the highest voltage on its input, and the other way around. I wanted no LEDs to be turned on when I have high resistance on the input. High resistance on the input means high voltage for our signal, and well, if I would feed it into LEMET 3915, it would do the opposite. It would just turn on all the LEDs. So I needed this reversal to be happening. Okay, so this is why the third op-amp is required here with all its associated components. On top of that, it's not just a reversal that I need, I also needed for the input to output voltage to take this kind of a curve. Because if I am to set a reference voltage of 2 volts for LEMET 3915, considering it's each LED is 3 decibel apart from the other LED, then these are the voltages at which each LED turns on. So if I plot the input voltage that I get against the voltage that this integrated circuit requires, then I need to have this particular curve. Okay, this is why I needed to basically change the signal to take on this shape. So once I do that, that's pretty much it. I can feed it to this integrated circuit. This circuit only needs 2 resistors. Maybe I'll make a video in the future about it, although I'm pretty sure if you search LEMET 3915 on YouTube, you will find videos about it. There's one resistor that helps with setting the current for these LEDs, and I've chosen 5 milliamps for each. And also both of these resistors are necessary in order to provide 2 volt reference voltage to be used internally by this circuit. Okay, so that it can compare that 2 volts reference voltage with the input signal essentially. And this drives all of these LEDs and turns on and off all of them in accordance with whatever happens with the signal. Okay, now we needed to do a few more tricks, and that is basically in order for these LEDs not to burden too much this transistor, I didn't want it for the current through the LEDs to pass through this transistor, but rather to come directly from the battery. Sadly, I cannot simply connect their anodes to the positive rail of the battery, because then due to the internals of LM3915, they will get to be turned on more or less randomly and constantly, you know, which is a problem. So I needed to power them, to cut power from them whenever I don't need to have them powered. So this transistor that basically feeds all of these other circuits is also commanding the base of this T8 transistor, and whenever it turns it on, the T8 transistor connects the anode to the positive rail of the batteries. Otherwise T8 is shut down and the anode is not connected at all. Okay, and on top of that, besides the visual aspect, I also wanted a buzzer to sound an alarm whenever I have around 5 ohms of resistance. So I've chosen to take, well, and in my case it turned out to be 6 ohms, but this is easily changeable by simply connecting the associated output pin of LEME 3915, the one that's associated with the desired resistance, connecting it to the fourth op-amp that works as a comparator, and we have here a voltage divider, such that normally the op-amp stays with its output high, and therefore T9 is blocked, and whenever that particular LED gets turned on, in order to be turned on, its cathode is being brought to the ground. This makes it so that the voltage on the minus input of the op-amp is higher than the one on the plus that comes from the LED, and so this op-amp's output gets to be pulled down to the ground, which in turn turns on T9 transistor, which in turn, you know, turns on the buzzer, and the buzzer just makes an annoying sound essentially. So that's pretty much about it when it comes to the design of this particular continuity tester, which can resist up to 400 volts on the input both ways, and yeah, it provides a lot more functionality than the other continuity tester. It's also a lot more complex and requires more work to build it. Okay, so now let me show you a few things about how it works and how it behaves, because it behaves differently for different voltages on the input. So let's start with the beginning. If we apply a positive voltage here, positive to the pin, negative to the ground, between 0 and 2 volts we will have the first LED of the continuity turned on, and that's something that we will just have to live with. Between 2 and 5 volts we see that there are no more LEDs being turned on the continuity, but we are starting to see the voltage alarm LED, let's call it like this, start to turn on. Okay, it is barely visible here, but the green LED is actually very faintly turned on at 5 volts and something. At 10 volts the LED is turned on enough so we can clearly see him, and at 20 volts or above it is turned on even more, so it's much more visibly turned on. Now if we apply reverse voltages up until some 14 volts, we will have all of these LEDs from the continuity tester turn on, and therefore the buzzer will also sound. However, at the same time we will also see the red alarm LED being lit, this will clearly indicate us that we are not actually having a continuity, but we're actually having a voltage on the input that shouldn't really be there. Okay. Above 14 volts, we no longer have the continuity LEDs turned on, and we keep having the red alarm LED turned more and more. Okay, at 27 volts, we clearly see the red LED being lit pretty well. Okay, what else? Right, so if I place a voltage, a voltmeter, on its inputs in order to measure the voltage that we see about 2.9 volts, which is good enough. It means that it will not blow away 3.3 volts digital logic circuits. And that's pretty much it when it comes to how it behaves for voltages. Now let me show you how it works in practice. I have two videos here along with the associated sounds. So here we have a 220 volt circuit. Okay, by the way, if you do this at home or anywhere else, you do this at your own risk. We have a 220 volt circuit that powers a light bulb, and we have exposed wires so that we can connect this continuity tester both to a wire so that we measure continuity, and also to the other wire so that we apply voltage and see how the whole thing behaves. Okay, so here I'm connecting first to the wire to make it work as a continuity. It takes a while for me to make a firm connection, electrical connection, but once I do it, we see that it works as expected. And then when I'm applying voltage on the input, we see that basically we have the two alarm LEDs turned on. Okay, we also have the first LED in the continuity turn on. That's just a byproduct. It's not a problem, it's okay. The alarm LEDs have a higher priority, to call it like this. Okay, so the alarm LEDs tell us that we have voltage on the input instead of a resistance, and also the fact that we have both of them lit means that we have an alternative voltage. Okay, and then I test to see that everything works with the continuity as well, which basically proves that nothing blew up, nothing has been broken. So the continuity tester, just like in Leo's design, can definitely resist dangerous voltages. Okay, so that's pretty much it. And also there's another aspect that might be a bit I don't know, unpleasant for some people, and that is the fact that in order for it to work completely, you have to give it about half a second time. So it's a slow continuity tester. Okay, and this is better seen in this particular video. Notice how after I connect the wires together, it takes about half a second or more for all of these LEDs to turn on and for the buzzer to start beeping. Okay. However, also notice that as soon as I connect the wires, we have a very short beep, and the first LED of the entire VU-meter lights up instantly. This is a way in which we can definitely know that we have some continuity instantly. Okay, so it does have a partially instant reaction, but if we want it to work fully as expected, we need to give it about half a second of time. This might be annoying for some. It's not a problem for me, you know. I don't need to test continuities constantly all of the time, so I definitely don't have a problem with waiting half a second for something to see if it is continuous or not. Okay. And okay, one more thing I see useful for me to show it to you, and that is how exactly do these LEDs turn on, because I've tested them with individual resistor 1 ohm resistors, and these LEDs turn on kind of like this. The first LED turns on and stays on anywhere between 17 and 18 ohms. The second LED between 14 and 16, third LED between 11 and 13, fourth LED between 7 and 10 ohms, and then kind of like from 1 ohm to 1 ohm almost. The fifth LED turns on at 6 ohms, the sixth LED turns on at 5 ohms, seventh LED at 4, eighth LED at 3 ohms, the ninth LED stays lit when it's 1 or 2 ohms, and we only have all of these 10 LEDs turned on when we have around 0 ohm resistance. So below 1 ohm of resistance is required to turn on all of the 10 LEDs. Okay, I consider this to be a good enough answer, a good enough response, okay, in terms of the feedback that this device gives us. And so I am overall content with the circuit, with the results. It is definitely doing a great job. I definitely managed to succeed in having more that Leo had in its continuity tester. So yes, overall I am very glad of this particular design. So that's about it. I hope you found it useful as well. If you would like to build this, I will place all of the files, all of the project files in an archive on Patreon. If you would like to download them and create them yourself, be my guest. You have their PCB schematics as well. So thanks a lot for watching. I hope you found it useful or at least interesting. Please like and subscribe to my channel if you would like to see more of these videos in the future. Also, if you would like to support my work so that I can keep designing, building, and presenting to you newer and newer devices, please consider becoming my Patreon on Patreon. Helping me financially definitely means a lot. By helping me, you basically help yourself, because the faster I can buy components, devices, the faster I can learn new things, and the faster I can come here and teach you as well, so that you don't have to spend so much time and energy studying those things yourself. So thanks a lot for watching, and I will see you in the next video. Bye bye.